Hello, welcome to the NCL Land-Based Railway Cyber Twin training video. Today, we'll be focusing on one of the many ways you can attack the railway system. So, here is a quick overview of what you will gain from this video. We'll be exploring Ettercap and its capabilities, as well as what ARP Cache Poisoning is, and how to carry it out. We'll also be looking at how Modbus packets are constructed and how they can be analyzed, then modified to suit our purposes. We will assume that you have a basic understanding of what a network packet is and how they are routed. By the end of this video, you should be able to carry out an ARP cache poisoning attack on the railway system and be successful in modifying the Modbus packets on the fly for incoming or outgoing packets. Now, let's look at exactly what we'll be covering in this video. Firstly, we'll be going through what Ettercap is and how it is useful to us. Next, we'll be looking at what it is that the address resolution protocol is and how to poison the ARP cache. We'll briefly go through the changes made to the network diagram for this workshop and what we will use before going through a demonstration of ARP cache poisoning on the railway. We also touch on how to analyze and modify Modbus packets into the railway system through another follow-up demonstration. So, what is Ettercap? Well, Ettercap is a network analysis tool, a typical tool used in man-in-the-middle attacks. It comes pre-configured with ARP and DNS spoofing and HTTP and HTTPS interception attack structures. But why do we use Ettercap instead of writing and executing the code from scratch? Well, Ettercap helps to simplify the actual network analysis of host discovery and host targeting and so on. The GUI allows us to perform attacks with minimal effort, as the attack has been mostly coded for us. The simplicity and reusability of code helps us to spend more time focusing on the attack itself and analyzing the system rather than spending time on low-level code. So what can Ettercap help us to do? Ettercap can scan for all connected hosts within the subnet, allowing us to view their IPs and handpick which host to target for our attacks. This can also help us analyze the function of each host by analyzing their incoming and outgoing packets one at a time. If we were not provided the IPs of each HMI and PLC, this is one way to discover their IPs and functionalities. Ettercap filters allow us to monitor and restrict the traffic flowing through the filters. This can be done using simple if-else statements that are written like C code. More information and functions can be found on the Etterfilter man page. One such use case is to drop all packets if they fit the regular expression regex stated in the Etterfilter. These Etterfilters are also more than just filters, they are scripts as well. They can partially or fully replace data in the packets, as well as create completely new packets to inject based on the current traffic. Moving on to ARP, the Address Resolution Protocol is a communication protocol for hosts to map the IP addresses of other hosts to the correct MAC addresses. While IP addresses help devices find each other across networks, the actual delivery of data within a local network relies on MAC addresses. This mapping of IP to MAC is stored locally in the ARP cache. Every server, host, or router will constantly send ARP requests to its local subnet. This helps to update the ARP cache if there are any new hosts to map, or if there are any updates required for the local ARP cache. These ARP requests are broadcasted, and all hosts within the subnet will receive these requests. The animation here helps to illustrate how an ARP request and response works. So every ARP mapping entry of IP to MAC is either dynamic or static. If a mapping entry is dynamic, this means it is subjected to changes and will update if an ARP request response states that the MAC address retrieved is different from the current ARP cache. The cache entry will then update to match the ARP response. If a mapping entry is static, the ARP request is not sent out for the IP. The only way to change the entry's MAC address will be manually configuring the host ARP cache. You can use the command ARP-A to view the local ARP table. If the ARP command is disabled, then IPN will also work. Right, now let's go through a quick recap of the railway network. For the engineering department, remember that there are 4 VMs for controlling the PLCs and 1 VM for controlling the RTU. Today, we'll be focusing on the train control PLC VM, which are for PLCs 6 and 7. These PLCs are responsible for controlling the third track power input switch, which provides power to the trains. There are also 3 HMIs in the operational room subnet, and each controls a different part of the railway. Note that for this workshop, we have added an attacker VM to the subnet. You can take this to be a staff computer working in the operational room, which has been compromised in a prior IT attack. This attacker VM will be where you RDP in and conduct your attacks from. We'll be focusing on using this attacker VM to target the train controller HMI for this workshop. Now, the ARP communication protocol was created in 1982 without a security feature in mind, since the focus was on speed and not security during that era. Therefore, dynamic ARP responses are not validated and can actually be easily faked. By sending out false requests and responses to ARP requests of the target, an attacker can intercept all incoming and outgoing traffic. The attacker can pretend to be target 2 when communicating with target 1 and pretend to be target 1 when communicating with target 2. This way, both targets are not made aware that a third party is monitoring their conversation. This positioning of the attacker between 2 targets is where the man in the middle attack gets his name. So how exactly does the attacker position itself between the 2 targets? Firstly, the attacker pretends to have a different IP, for example the gateway's IP. This means the attacker sends ARP requests to the target, stating that the gateway's IP should be associated with the attacker's MAC address. The attacker also sends ARP responses to the target's ARP requests with that same idea. We will not be covering ARP collisions in this workshop, since Ettercap takes care of that for us. Once the ARP requests and responses are handled, the target's ARP cache should now be associating the gateway's IP address to the attacker's MAC address, instead of the gateway's MAC address. Thirdly, all the traffic coming from the target that is meant for the gateway is routed to the attacker instead. This is because the packets follow the target's ARP cache to find out their destination MAC address, to understand which host to travel to inside a local subnet. Lastly, The attacker receiving all the traffic from the target can now analyze and control the output traffic of the target. The traffic from the target is usually forwarded back to the gateway after modification. To control the input of the target, we can do all of these steps again by targeting the gateway instead. Okay, let's look at ARP cache poisoning in action. We'll be using the attacker VM as an entry point into the railway system, and our target will be the train controller HMI, which is at 10.107.121.6. Our end goal will be to convert all the local MAC addresses on the target's ARP cache to the attacker's MAC address. On the target VM, the train controller HMI, let's first check the ARP cache. So the ARP cache looks normal. Take note of the attacker's MAC address, where the attacker is at 10.107.121.9. Notice that the attacker's MAC address is only one single value and it is not copied over to the rest of the IPs. Alright, let's go back to the attacker VM. On the attacker VM, we want to first turn on IP forwarding. So packets that we obtain from the ARP cache poisoning get forwarded back to the gateway, but with the correct destination MAC address. So I'll open up a terminal. So when we conduct the man-in-the-middle attack later, we do not cut off the connection between the HMI and the PLC. We simply want to see what packets are being sent. So to enable IP forwarding, we first check whether IP forwarding is enabled. As you can see, the value is at 0. So to turn this from 0 to 1, we write it to 1. If you want to enable IP forwarding on startup, you can also do this for persistency. And now we can just check that our VM is properly set up to intercept these packets. So if we do netstat-nr, we should see the default gateway IP as 10.107.121.1, and the interface for that is at ETH1. Great. So let's go to Ettercap, and let's use the GUI version of Ettercap for learning purposes. You can use the CLI version if you want. So first, let's change the primary interface to ETH1, as that is where our VM is connected to the network with the HMI. And then let's click accept. So let's first click the menu at the top right, and under host, we now look at the we scan for hosts within our subnet. So now we can click the menu again, and under host, we can select host list and look at what we have scanned from the network. So our target is 10.107.121.6. So let's right click on that and select add to target 1. Let's now look at our target list under menu, targets, current targets. We can see now that 10.107.121.6 is now under target 1. So let's start the ARP poisoning. We can click the MITM menu right now and select ARP poisoning and click OK. So on the surface, it doesn't look like we have done much. But let's look at Wireshark and see if there's any changes. So on Wireshark, we capture on the interface ETH1, as stated just now. And since there's so many packets, we can just filter for TCP port 502. We can now see that packets whose source and destination are not from us at .9, but from our target at 121.6 is being passed through our VM. Great. Now let's look at the target's VM ARP cache now. So now, if I look at the ARP cache, notice that all of the IP addresses for the IPs in our subnet 10.107.121./24 have become the attacker's MAC address. This means that our ARP cache poisoning is successful. Okay, now that we have the target packets coming in, take some time to explore and analyze these packets by yourself before we dive into the analysis together. You can even try making your Ettercap filter now and see if it works. So after ARP cache poisoning, we can now see the target's outgoing traffic from our attacker VM using Wireshark. By Googling, we know that the standard TCP port for Modbus is 502, so we can filter for that in Wireshark. We notice that the Modbus communications have a query and a response, and the target VM is communicating with a destination IP 10.107.108.8. We can assume this to be the train control PLC VMs for PLCs 6 and 7. By analyzing the query packet, we can observe patterns in the packet structure. Take note that the Modbus data we want to analyze and modify is in the last few octets of the packet's bytecode. The Modbus data we are focusing on is the function code and the reference number. Now, looking at the whole Modbus packet, we notice the following. For the Ethernet frame, the source or destination MAC address has been changed to the attackers. This is intended and is the result of the ARP cache poisoning. There are no changes to the IPv4. For the TCP segment, we notice that the Modbus requests have a destination port of 502, and Modbus responses have a source port of 502. The picture shows a Modbus request. At the Modbus TCP layer, we notice that the protocol identifier for all Modbus communication is always 0, and the unit identifier is always 1. While the length varies for Modbus responses, the length is always 6 for Modbus requests from this HMI. This length will be different if multiple registers or coils are being set, but you cannot do so from the train controller HMI. For the Modbus data layer, the function code denotes the type of request, whether it's a read register or set single coil or so on. The reference number detects the offset from the 0th register or 0th coil. For example, a reference number of 5 refers to coil 5. Alright, let's try filtering for a set single coil Modbus request for the 6th train and turn the power on switch to power off. To filter for Modbus, we can set the Ether filter to only look at packets that are using the TCP protocol and have a destination of port 502. To ensure the packets are using Modbus, we can then search within the packet bytecode for a protocol identifier of 0, a length of 6, a unit identifier of 1. We also filter for the set single coil function code, which is 5. Lastly, to check for the 6th train, we check that the offset is 5, which corresponds to coil 05 for the 6th train's third rail power input switch. We can then replace the on with off by changing the FF to 00. Let's look at this ether filter in action. Our end goal will be to make the power on button for NS line 1 on the train controller HMI to become a power off button. Alright, so let's open a terminal and navigate to the desktop directory, just for convenience sake. So here we'll create an ether filter file, right, for us to write the logic for the ether filter. So I'm going to use Vim, but you can use Vim or Nano to edit the file. Alright, so let's first filter for Modbus requests using TCP and having a destination port of file2. So if ipproto equal to TCP, right? So next, let's search if the protocol identifier equals 0, the length is equal to 6, and the unit identifier equal to 1. We also want to search if the function code is equal to 5, which is for set single coil. So we can just do this, where the if search for the data, which we are searching for the binary data. So first, we want to look for the protocol identifier, which is 00. We can see this from our Modbus query request in Wireshark. Then we want to search for a length of 6. Then we want a unit identifier of 1. And lastly, the function code of 5. Right, so this should be it. Okay, for the next step, we also want to look for the reference number is equal to 5. So we are targeting the 6th train, which is NS line 1. And you can find out which train corresponds to which reference number by observing the Modbus request, or simply seeing from the train controller HMI that the 6th register and the 6th coil correspond to NS line 1. So here, I'll be looking at the 5th reference number. And I can even put a message here to make sure that I understand that this is for train NS line -1. Right. So for the next step, we want to replace the request for turning on with turning off the train instead. So here, we could do if replace. And here, instead of FF, which is for turning on, we can replace it with turning off. So turning off would be 00, right? So this, we could simply say that we cannot start the train NS lying -1. Right. So with that, we should be done writing the filter. Again, we only know all of this information by first inspecting and analyzing the network traffic to understand how the Modbus requests are processed and what data corresponds to what values. Right, so now that we're done with writing the filter, let's compile it into a readable format for Ettercap. So we're going to do Etterfilter, and we're going to output it into a file called, let's say, filter.ef. So there's a syntax error on line 7. So over here, I forgot to remove the spaces. And it should be done. Right, so we'll copy this compiled filter to the folder which Ettercap finds its filter from. So this is not necessary, but it makes our life easier to organize all the compiled Ettercap filters into one place. So we just cp filter.ef, and we're just going to pass it all the way to the Ettercap's place where it finds the filters from. And for this, we'll just rename our file to maybe droptrain-attack.ef so that we know what this filter is for. Right, so let's return back to Ettercap, and we'll just stop the man-in-the-middle attack temporarily. Great. So now we'll just load our filter by doing menu. We go to filters, click load a filter, and selecting the filter that we just made, which is drop train attack, we click OK. Great, and we can see that the content has been loaded. Now let's turn back on the ARP poisoning. Can you see that it works? So now if we go back to the target, the train controller HMI, right, we can see that our ARP is still poisoned. And notice that if we try to turn on the train NS line 1, it shuts down the train instead. So you see that the power is instead off instead of on. And in fact, whenever we try to do this again, it will simply not work. So this means our attack was successful. This workshop is meant to be a simple introduction to how to attack the railway system. Please feel free to explore and develop more advanced attacks on the railway system. If you would like to familiarize yourself more with Modbus, try swapping random power on with other trains' power on buttons or even power off buttons. You can also try using other tools like Ettercap and Scappy to route traffic to different IPs and ports so that you can conduct more detailed and custom packet modification and forging. Other HMIs, VMs, and even other subnets like the engineer subnets can also be targeted, or even other protocols like S7COM. Okay, that's the end of this attack workshop. I hope you can now understand and carry out an ARP cache poisoning attack on the railway system. In addition, I hope you can view, analyze, and modify the target's Modbus packets while they are passing through the attacker VM to execute a successful man-in-the-middle attack. Thank you.